Hi, everyone. Welcome to my talk on MLOps for GraphML. So before I jump into the content, I just wanted to quickly introduce myself. So I'm currently working as a principal solutions architect at AWS. And although I am working at AWS, my talk today is just generally about MLOps concepts for graph databases. So it's not really specific to the AWS cloud. At AWS, I'm working with customers both in the field of analytics as well as machine learning. Some of my other background you can see there, so I've co-authored a book on some machine learning best practices using some of the AWS tooling. I've spoken at some other conferences like this one. I've actually got a reasonably long background in machine learning dating back to my college days, working on self-driving golf carts back when the state-of-the-art computing resource we had was a 46 PC, so that was a lot of fun. In some of the areas I'm actively working in now based on what I'm seeing with some of the customers I work with, GraphML, certainly one of them, seeing them come up a lot in fields like identity graph. And then reinforcement learning is another area. So my LinkedIn profile is up there on the screen and happy to connect with anyone who's watching this. So in this talk today, we're going to talk briefly first about just MLOps in general. So if you haven't run into that, or if you've heard of it, but not really sure exactly what it means, I'll just give a quick introduction to MLOps. And then I'm going to talk what is unique about MLOps when it relates specifically to machine learning models that we built using graph neural network techniques. So using the data from a graph database and using GraphML. And I'll also talk about how to overcome some of those challenges. So let's get started by talking a little bit about MLOps in general. So MLOps has a lot of conceptual similarities to how DevOps started, what was about 15, 20 years ago now. And if you recall, DevOps was really about breaking down the walls between the folks that wrote software and the folks who actually ran it in production. And some of the motivation for that was improving quality, getting rid of the problems like it works on my laptop but it doesn't work in production, increasing the cycle or speeding up the cycle time. So in other words, being able to deploy things more quickly as well as with higher quality. So what's interesting about MLOps is we have a lot of the same challenges, but now we have a new persona involved. So there's still DevOps folks or software engineers involved in a lot of machine learning projects, but you also have data engineers, so the folks who understand how to work with and move and analyze large data sets that typically feed into a machine learning process. And then we have data scientists. And each of these three groups of folks have their own preferred tools and ways of working. And one of the big problems that we've seen with machine learning projects not making it into production, or at least not making it into production as quickly as we'd like, is this kind of lack of efficient ways of working between these three groups of people. So data scientists may prefer to work in their Jupyter notebooks, do some quick experimentation. Data engineers are maybe working in the Hadoop and big data ecosystem. And then, of course, software engineers may be working in containers or serverless functions or something else. So three very different mental models and ways of working. And MLOps is really how are we thinking about making sure that these three groups of people can work together effectively and make sure that our machine learning projects can make it into production in a way that's repeatable and reliable. So solving some of the same problems we had with software when DevOps came onto the scene. Now we've got MLOps. And so we've put together this mental model of stages of MLOps adoption. And where most people start is at the project phase. So you start up your first machine learning project, you have your data scientists working, they produce a model, they're interested in getting their proof of concept done quickly, so that's the thing they measure. And then they go to say, well, this model is good. Now we want to put it into production. What happens next? And so you may think, well, just turn it over to the DevOps people. But there's a couple of interesting challenges with machine learning projects. So one, in DevOps, source code is our key input. It's really, along with maybe tracking our build artifacts, source code is really the only important input we have. In MLOps, our important inputs include not only source code, but also the data. And then we may need to reproduce our models just based on a calendar as new data comes in, as well as when we make changes to our source code. So then the next phase is making things more repeatable. So what we're looking here is reducing the model deployment time. So, when the first work in the project phase, we might have this kind of awkward handoff of, hey, here's a model, let's hand it off to the people who know how to run things in production. And there's a lot of back and forth that goes on there. So in the repeatable phase, we may invest in some automation, some monitoring tools to make sure that at least when we get a model built, we can deploy it consistently all the time. Then the third phase is focusing on reliability. And here what we're looking to do is reduce the defect rate. So things like, we deployed this model, but the data that's coming in when we try to get a prediction doesn't really look like the data that we trained on. So we may have some software bugs introduced. And so here we're trying to integrate a machine learning development lifecycle throughout the project. So we're looking at different deployment patterns like blue-green deployments or A/B testing to test out different versions of our model. And we're investing more in automated monitoring. And then finally, where we'd like to get is the optimized phase, where the entire machine learning development lifecycle is reproducible and automated. So our data scientists can focus on the data and the model, what they do best, and there's a lot of automation to support that and make sure that the deployment into staging and production environments is reproducible and automated and high quality. So the metric that we're looking on there, which is really what the business cares about, is how do we reduce that overall cycle time? So from the time our data scientists start a new machine learning project, how quickly can we get the thing into production, not just to the point where we have a trained model? So with that big picture in mind, just to show you where some of the deployment complexity comes in, this is a reference architecture that shows conceptually some of the different pieces involved in building an MLOps system and lifecycle. So where you can see we have our input data, which is our data, which can become either from batch sources or come from streaming input. Our other inputs are the source code that we use for data preparation and for preparing the model. So we may have a data pipeline that assembles these things into our data lake. Then data scientists will work and go through their experimentation. So there's often a formal experiment management system here. We produce our artifacts. We go through model training. We'll be evaluating how well the model performs using data science specific types of metrics. We'll be recording the model in a model registry. So you can think of it as just a special type of artifact repository that has some specific features that are useful for the type of things that machine learning projects produce. And then we'll deploy the model into production. And that may mean that we get a bunch of predictions all at once, or it may mean that we host our trained model in an inference endpoint. And you can think of that as being a microservice endpoint. So in some sense, it's just a software endpoint, and it may have serverless functions behind it, or virtual machines, or containers. And then, of course, we need the appropriate monitoring in place. So over the last few years, there's been a lot of tooling developed to help make MLOps easier, or at least easier to get started. These include more or less complete MLOps frameworks. Some of those are open source, like Kubeflow and MLflow. There's some vendor-supported ones. So for example, H2O.AI has a popular MLOps framework built into their product. Of course, AWS has a lot of these services and solutions as well. And then for individual pieces of that broader MLOps picture, you'll find point solutions for things like workflow orchestration, feature stores. Feature stores, again, you can think of them as very specific types of artifact or data repositories that track the data after we've done some initial processing on it to make it ready for machine learning. And then, of course, experiment tracking as well. And this is by no means an exclusive list, by the way. This list is growing. It gets bigger every day. So with that brief background, now let's look, well, what's unique about MLOps when we talk about graph machine learning, and then how do we overcome some of those challenges? And it's worth noting here just briefly that if you look at the history of machine learning, before we had deep learning or neural networks, there was some very, powerful and well-proven techniques to do things like regression or classification for things like customer churn prediction. And then we had our first generation of neural networks that were useful for the same types of tasks, but had a much different internal architecture. Then we had, you'll see different variants of these neural network architectures being built to solve specific types of problems. So for example, if you're doing image analysis and you want to detect specific types of objects in an image, there's a very specific type of neural network architecture called a CNN, a convolutional neural network. And it's designed to take advantage of the information that's contained in the structure of the image. And just like we have those special types of architectures for images and for natural language processing and other types of tasks, for the data that we have in graph databases, and that's of course very different from what you have in a relational database. In a graph database, the information contained in the edges, in the relationships between two different things, is often as important as the properties of the nodes or vertices themselves. And so there's a new type of neural network architecture called a Graph ML model, or a GNN, Graph Neural Network, that's designed to exploit that information for tasks like predicting the relationships between two vertices or classifying a particular edge or a particular vertex. For example, if you're tracking health insurance claims data in a graph database, it may be very interesting to predict whether a particular healthcare provider is, maybe committing fraudulent activity, submitting claims that are fraudulent. And there, it's not a particular healthcare claim or bill that we're looking at. It's the pattern over time of the relationship between that healthcare provider, the patients they see, and the type of procedures they do. And it may only be a very small percentage of the claims that are fraudulent in some way. So, what this slide is showing is that one of the challenges we face is that compared to a traditional type of ML scenario on the left, where our data may be stored in a data lake or in a data warehouse, and we have some common tools like pandas and NumPy and Spark to analyze and work with that data. When we're working with Graph ML, our data often comes from a graph database, and our data pipelines then have to know how to work with the data in that graph database. So we have to use popular tools like Sparkle, Gremlin, OpenCipher. And if we're trying to plug the data from our graph database into a data pipeline in our MLOps framework, then the tools we use in that pipeline, like Spark, have to have connectors that know how to interact with the graph database. So the recommendations I have here are pretty straightforward. We have to start thinking of the graph database as a first-class part of our data lake. And that means that our ETL pipelines and our analytics tools have to be able to work with the data in that graph database. And for larger data sets, when we are interacting with, say, big data tools like Spark, we have to make sure that we are configuring those properly to take advantage of parallelism for example, exporting and preparing a large amount of data from our graph database. The next area I want to touch on is orchestration. So if you think about all the steps involved in that MLOps pipeline picture that we saw a few slides ago, there's a lot of steps involved, everywhere from taking data from our data lake, doing our initial feature engineering, building a model artifact, testing that model, deploying it to a staging environment, and so on. So the common tools that we use for that orchestration, and this could be everything from a CI/CD tool to Apache Airflow, these often integrate well with common data sources and the tools we use as part of data engineering. But they may not always integrate easily with the specific tools and connectors and data sources we have when a graph database is part of the picture. And so we may have to make sure that the pipeline tool we use is very easily extensible so that we can include different data sources like our graph database and different types of processing steps. And so what you may find here is that it's easier, rather than using one of the purpose-built MLOps orchestration tools like Kubeflow pipelines, you may find it easier to use a more general purpose orchestration tool like Apache Airflow. That's a very common open source one found in the big data ecosystem. AWS Step Functions is another general purpose orchestration tool. And the picture you're seeing there is actually just an illustration of the MLOps pipeline I built for a graph database as an example for this workshop. The next area I want to touch on is explainability and data quality. So explainability is a really hot topic in machine learning, and it has been actually for the past at least 2 or 3 years. And I think that's for a couple of reasons. So first, a lot of business stakeholders have a hard time trusting a model that's entirely a black box. They'd like to have at least some intuition about why a model is behaving a certain way. For example, if you're making loan decisions based on a machine learning model, it's important to have some sense of why a loan for a particular applicant is rejected or approved. And in some cases, that may be a regulatory requirement to be able to explain that. So there's been a lot of work on explainability. And there's some well-proven techniques now for working with tabular data. So you can think of data coming out of a spreadsheet or a data warehouse where we're doing something like sales forecasting or loan approval, things like that. For other domains like computer vision and natural language processing, it's more of an emerging field, but there has been good progress made. And a lot of the common algorithms like SHAP can now be used for computer vision and natural language processing as well. But this is very much an area of active cutting edge research for graph ML. And on a related note, a lot of times we want to be actively tracking our data quality as well. So one thing that happens to machine learning models over time is you may see data drift. So the nature or the statistical distribution of the data coming into your prediction endpoint changes over time as your customer behavior changes or business conditions change and so on. So it's really important to be able to track data quality over time and make sure, does the data that's coming in for predictions, does it look similar enough to the data we use to train our model? And again, for a lot of traditional ML scenarios, there's some rich libraries and open source tools available for that problem. But again, a lot of those libraries don't really understand graph data, at least not natively. And so it may be difficult to get a sense of data drift when you're talking about a graph database. So what can we do to address these problems? So first of all, in the area of explainability, there's not really a one-size-fits-all answer here. There are graph explainability projects out there they started a few years ago in the academic field. Some of them have open source implementations now and are slowly being adopted into some of the open source graph ML frameworks like DGL, which is the Deep Graph Library. GNN Explainer is one that I've come across a few times. It seems to be a pretty good option. And again, it's integrated with some existing frameworks like PyTorch Geometric and DGL. And that snippet of code there is just showing what it looks like to use the GNN Explainer. What it's really doing is trying to give you a sense of looking at a particular, say, vertex in the graph. How important are the relationships to neighboring vertices? So how important are those edges? And how important are the properties both of the vertices and the edges in explaining what that graph ML model is actually doing? Now, on the data quality front, again, there's not really a one-size-fits-all answer here. You can take a couple of approaches. For example, if you export your graph library into a tabular format, into flat files, in an object storage system, there are open source libraries like DQ that can then go and look, for example, at least at the properties of vertices and edges in isolation and give you some statistical information about the data distribution and quality there. What's probably more interesting, though, if you think about, maybe what we want to track in terms of data drift are some graph-specific metrics like connectivity scores. And you can think about all the different types of graph algorithms that are built into most graph databases to look at, neighborhood scoring and clustering and connectivity scores. I would recommend at least starting to track a few of the basic ones. Just track them over time as your data changes and see, are the connectivity scores for most of your nodes changing? Are they increasing or decreasing? Now, there'll be a lot of art, probably more art than science in this for at least another couple of years. But at least it's a place to get started on at least tracking some data so we can see if there's any interesting trends over time. So just a couple more areas. So the next one is the feature store. So the reason the feature store is interesting for machine learning, a very common first step in an ML workflow is to do what we call feature engineering. We take raw data and we turn it into a format that's usable for a machine learning training job. In some cases, that's very straightforward and fast. In other cases, it can be quite complex and it can take a very long time. For example, if you're using a state-of-the-art natural language processing ML framework to build your own, say, language translation service, preparing the features can take hours, even on very powerful hardware. And so the feature store is a place where we can store those prepared features, share them with other teams, reuse them, and also use them to make predictions when new data comes in. And so these are becoming very, very predominant in machine learning ecosystems these days. But again, feature stores were mostly designed to store prepared features in either a tabular format or at least in a key value paradigm. And so they don't naturally align with how our data is structured in our graph database, where our features include not just the vertices themselves, but also the relationships or edges. And so my recommendations here would be a couple of things. So first, you can maintain your lineage in your graph database. And second, as an option, you could export data from your graph database periodically to your storage system or to your data warehouse and track it as features there. Once it's exported as a set of flat files, say with one set of files tracking the vertices and another tracking the edges, then it's a little bit easier to ingest it into a feature store. And then the final area I want to cover is the inference format. So what happens when we actually have a model built and we want to get a prediction? So with typical models, what we're passing in are rows of tabular data or sentences for natural language models or images or video. And in some cases, we may need to have an inference pipeline that does some of the original feature preparation before we make the prediction. So for example, with natural language models, we often need to do a lot of work to take an input sentence and convert it to the format that the natural language model understands. And so we'll often have, if you think of just the steps in this pipeline as containers, we may have a first container that does that data preparation, and then the second container that actually makes the prediction for us. This becomes more complex when we're dealing with graph machine learning, because with most popular neural network-based graph ML frameworks, making a prediction requires knowledge of the neighbors around a vertex and often other embeddings that we've computed. And so if you actually look under the hood at what's happening when you get a prediction from most graph ML models, there's quite a bit of kind of middleware software in there to do this data preparation and conversion steps for you. And so this means that your inference pipelines can become more complex. And in some cases, I've even seen systems that just get all the predictions for all the data in the graph all at once, and then just store it for retrieval rather than trying to get it one element at a time. So again, the recommendations here, again, you often need to either build in a software layer that can do this intermediate data preparation for you before you get predictions, or again, you can just get predictions all at once in more of a batch mode right after the model is trained. So to conclude, I do have a working example I built. There's the link there. I know it's a bit of a mouthful there, but hopefully if you pause the video, you can grab a copy of that link. So this is a workshop, freely available. If you have an AWS account, you can use, and it walks you through building an MLOps pipeline using the AWS Graph Database service, which is called Neptune, as well as some other tools. The type of GraphML model it builds for you is actually based on the Deep Graph library. So it is based on an open source GraphML framework. So you may find that a lot of the techniques there are easily reusable even if you use other types of graph databases or other tools. And that brings me to the end of my session. So thanks very much. Really appreciated getting the opportunity to deliver this, and look forward to connecting with you over LinkedIn.